On November 28th, ThreeI Atlast reveals a version that NASA never wants you to know. ThreeI Atlast appears to originate from the HD 43782 star system, with an Earth-like planet following a narrow trajectory that seems to have been targeted 2 million years ago, and showing signs of arrival time adjustment suggesting an automatic Bracewell-style probe model. Observations by Webb show that inside ThreeI Atlast, there is a stable electromagnetic field with a power of 2.3 MeV, an outer shell with an exotic material spectrum, a surface with straight boundaries and symmetrical circular holes like assembled plates, an EM signal that changes exactly when the most powerful telescopes all look at it, and a timing ratio that matches precisely the Earth-Jupiter mass ratio, while the post-perihelion trajectory of ThreeI Atlast heads toward the Jupiter region exactly when the JUICE spacecraft is operating. Spectral and dynamical data further show that ThreeI Atlast has an enormous mass, is leaking water at an unusually high rate. Beyond the frost line is venting nickel without iron, like an industrial processing signature, carries an anti-tail and a chain of approaches to Mars, Venus and Jupiter, with an extremely low random probability undergoes record non-gravitational acceleration, brightens by a factor of 400 shifts, colour from red, green, blue in reverse of the usual rule, and still retains a durable core with 7 narrow gas jets after its sweep past the Sun. The mystery of ThreeI Atlast is gradually being illuminated, and right after this we will together with the scientists lift the veil on the identity of ThreeI Atlast in the latest research. Long before equations pinned down the path some minds began to picture ThreeI Atlast as more than a frozen wanderer. In those sketches, ThreeI Atlast becomes a slow, dark spacecraft, wrapped in a broad, durable shell that maximizes surface for absorbing light, shedding heat, or anchoring countless tiny instruments. Seen that way, the skin of ThreeI Atlast is not just crust, but a vast operating platform carrying sensors, antennas, and perhaps even habitats sealed away from vacuum. Speculation then stretches further. If ThreeI Atlast has travelled for ages through the thin dust between stars, ThreeI Atlast may have gathered traces of organic molecules, spores or more complex chemistry in hidden vaults, turning the craft into a drifting archive of possible life. From that perspective, ThreeI Atlast does not simply pass by Mars and Jupiter as landmarks. The visitor performs slow surveys watching thin Martian air and Jovian storms for signatures of atmosphere magnetism and any technology that might glow against the background. None of this can be read directly from a single line of data, yet the scale resilience and strange behaviour of ThreeI Atlast keep inviting such images. To test whether those images belong anywhere near reality, the next step is to stop guessing from the outside and trace where ThreeI Atlast might truly have come from. When astronomers rewound the sky, they treated time like a slow reversible film. ThreeI Atlast became a glowing frame on that film, stepped backward one calculation at a time. Using gravity simulations and N-body models, the team followed Atlast through the pull of stars and galactic tides. Across 2 million simulated years, Atlast drifted upstream against the sun's motion, like a quiet seed in a river. In most random trials, an interstellar visitor fans out into many possible birthplaces. Here the path of ThreeI Atlast narrowed, instead collapsing into a thin corridor in space. That corridor did not wander. It pointed repeatedly toward the same district of the galaxy, about 270 light-years away. Each refinement, each fresh dataset kept steering Atlast back into that small patch of sky. Some researchers called the pattern ordinary statistics, yet others felt unease at how focused the journey of Atlast appeared. They were not ready to speak of guidance or design, only to admit that chance no longer felt comfortable. In the quiet control rooms, screens dimmed, the numbers settled like dust in evening light. Far along that narrow corridor waited a star much like the sun, and the next question was what kind of world might circle there. The backward corridor of calculations narrowed until it intersected a single, unremarkable point of light on the galactic map. ThreeI Atlast, traced upstream for 2 million simulated years, kept returning to that same point, as if the journey were anchored there. Astronomers knew the star as HD 43782, a quiet G-type sun not so different from our own. Around HD 43782, models and measurements together outlined a third world moving through the temperate band where liquid water could persist, the same band ThreeI Atlast seemed to indicate. When that world crossed the face of its star, starlight filtered through a thin shell of gas and into the instruments. The spectrum that came back carried the fingerprints of water vapor, molecular oxygen, methane, and carbon dioxide existing side by side. In the language of planetary chemistry, those combined signals rarely sit still. They suggest ongoing reactions, a sky that refuses to settle, and 3I Atlast suddenly felt less like a random shard and more like a pointer. Under standard models, such an atmosphere should drift toward balance unless something keeps nudging it away. Some researchers calmly folded the spectrum of HD 43782 into their archives and called the overlap with the origin corridor of Atlast a coincidence of large numbers. Others stared longer, feeling that the same equations which led 3I Atlast back to this system had quietly drawn a circle around one possible cradle of life. In the soft glow of late monitors, no one could prove intention or chance, but the alignment between Atlast, the star, and the restless air of that distant world refused to feel entirely neutral. In standard models, a shard torn from a young system leaves like shrapnel thrown onto whatever path chance provides. 3I Atlast, under that assumption, is just one fragment expected to arrive from a wide and messy spread of directions. Natural ejections usually produce a fan of trajectories with energies and angles blurred by many small gravitational encounters. The path of 3I Atlast did not fan out. The reconstructed track clung to a narrow tube in phase space instead. To stay inside that tube, Atlast seemed to need a specific initial push, just enough to clear its home star and then coast for 2 million years toward our region. Within the models, the allowed starting speed and direction for Atlast clustered far more tightly than predicted for random debris. Some researchers argued that unseen interactions or incomplete physics might still compress those paths, keeping 3I Atlast inside the realm of natural outcomes. Others, staring at the same figures, felt they resembled the aftermath of a single decision, rather than an accident, as though Atlast had once been pointed. No equation on the whiteboard could prove intent, yet the contrast between a chaotic spray of shards and the focused journey of 3I Atlast became a quiet source of unease. To keep 3I Atlast on that narrow path, timing had to be almost impossibly precise. Any launch that sent 3I Atlast toward the future position of our Sun would need to know where the solar system would be, not just tomorrow, but 2 million years from the moment of departure. Gravitational tugs from nearby stars, drifting gas clouds, and the slow wobble of the galaxy all shift that future address, and 3I Atlast would have to thread through those shifts without constant correction. Small errors at launch grow into displacements measured in millions of kilometers, yet the reconstructed route of Atlast passes close by our system, instead of missing by a wide margin. In human practice, such long-range targeting would demand not only exquisite models of galactic dynamics, but the computing patience to follow every perturbation a standard 3I Atlast quietly seems to meet. Some scientists argued that unknown natural processes could still stack the odds in favour of a near miss becoming a near hit, while others saw the journey of Atlast as resembling a pre-written solution to a difficult equation. If a civilization once solved that equation, the same tools might also have let them estimate when planets like Earth become noisy with chemistry and technology. To minds bound to shorter timescales, the idea that 3I Atlast was launched toward a future where observers would be ready felt unsettling and oddly elegant at the same time. From the data alone, no one can tell whether this apparent foresight arose from chance, from deeper physics, or from a level of planning that to us would look very much like prophecy. In recent months, small changes in speed have crept into the path of 3I Atlast, as though arrival were being nudged instead of left to chance. Tracking shows Atlast shedding velocity in short, controlled bursts that are tiny on their own, but add up over distance. Comets driven by sunlight and outgassing usually stagger their pushes uneven, not trimmed the way 3I Atlast now seems to be. The pattern led several teams back to an old proposal from radio astronomy, the Bracewell probe, a machine sent to linger near developing civilizations. In that picture, a probe like Atlast drifts for ages and alters course, only when onboard sensors decide the locals have become technologically loud enough to notice a passerby. Seen through that lens, each new correction by 3I Atlast resembles a quiet decision to arrive when attention is hardest to ignore. To manage such timing after a journey of millions of years, Atlast would need structures that barely age and guidance that can keep watch without rest. Even if later measurements undo the Bracewell reading, the present behaviour of 3I Atlast already presses the limits of what we thought long-lived machines and autonomous navigation could do. One darker reading has quietly followed the data from the moment 3I Atlast was traced back to a living-looking star. In that reading, Atlast is not a messenger reaching out, but an instrument sent to watch, to record, and perhaps to judge. The long coasting phase of 3I Atlast and the recent trimming of arrival time fit that picture. No observation shows that Atlast offers greeting, and no result rules out a colder role. To minds raised on human stories, the first impulse is to imagine kindness, curiosity, or hostility inside 3I Atlast, as though the object shared our motives. That habit of anthropomorphizing Atlast may be the most dangerous assumption, because a civilization that plans across 2 million years may think in ways with no parallel in our history. From a more unsettling view, Atlast could be evaluating whether worlds like Earth remain background scenery or become part of some larger design. For now, the only firm ground is that 3I Atlast arrived from a specific place, appears to have been sent on purpose, and remains active after an almost unimaginable wait, leaving in tension as a question hanging over the data. When the James Webb Space Telescope stared into the hollow region of 3I Atlast, something close to impossible appeared. Instruments watching 3I Atlast reported a strong ordered electromagnetic field filling that internal cavity. The signal from Atlas sat in the extremely low frequency band between roughly 3 and 30 kHz, a range more familiar to submarine radios than to distant comets. Power estimates for the field inside 3I Atlast clustered around 2.3 megawatts sustained rather than flickering. Natural cosmic sources that produce radio waves from flares to pulsars usually spray many frequencies and drift in strength, a behaviour missing in the signal linked to Atlast. Lightning in planetary atmospheres crackles and dies, magnetospheres pulse and wobble, but none of those match a stable narrow band field quietly anchored to an interstellar visitor. As the data accumulated, the geometry of the field appeared to align with the spin axis of 3I Atlast, as though coils or structured plasma were guiding the energy. Teams rechecked calibration pointing and background noise to see whether the apparent beacon around Atlast might be an instrumental ghost. Those checks returned clean, leaving the field as a property that had to be assigned back to 3I Atlast itself. At that point, comparisons to a compact fusion system or some other controlled power source became difficult to avoid, even when the language in the report stayed cautious. A reactor of that scale tucked inside Atlast would rival small terrestrial power plants while resting in a dark, airless cavity far from any grid. For researchers used to inert chunks of rock and ice, the idea that 3I Atlast might host a persistent engineered energy core felt both elegant and deeply unsettling. If the interior of 3I Atlast truly holds a long-lived generator, rather than a chance fluctuation, the classification of the object shifts abruptly from a frozen relic of formation to a functioning piece of technology adrift between stars. The first surprise came not from the hollow inside 3I Atlast, but from the skin of Atlast itself. Spectrometers watching sunlight and infrared glow bounce off the surface of Atlast expected the familiar fingerprints of water ice, frozen carbon dioxide dust and common organics. Instead, the dominant absorption bands on 3I Atlast refused to line up with any standard mixture of ices and minerals catalogued in laboratory libraries. Across multiple wavelengths, the outer shell of Atlast behaved as though common volatiles were present only in trace amounts, riding on something denser and stranger underneath. Analysts cycled the data from Atlas through databases of terrestrial rocks, meteorites, comets, and synthetic materials looking for a near match. No combination of known compounds reproduced the depth and spacing of the features coming back from 3I Atlast. Even when models allowed for exotic temperatures and pressures, the spectrum of Atlast remained offset, as if the lattice of the material belonged to a different reference set altogether. Some teams proposed that unmeasured phases of carbon or silicates might occupy the shell of 3I Atlast phases that only form under conditions that are hard to maintain on or near Earth. Others considered a sharper possibility that the crust of Atlast might be assembled from engineered matter tuned for strength, endurance, or shielding, rather than shaped by slow condensation. Under that view, 3I Atlast carries a surface chosen to survive dust radiation, and time not a random rind left over from formation. The periodic table does not break when faced with a puzzle like Atlast, but the comfort of thinking we have sampled every useful arrangement of atoms does. With every pass of a spectrograph, the shell of 3I Atlast quietly argues that either our chemistry is incomplete, or someone somewhere has already pushed the design space of matter much further than we have. Before colour and shine, the shape of 3I Atlast began to raise its own quiet questions. High-resolution infrared images of 3I Atlast did more than trace a rough, irregular lump of rock and ice. Across the surface of Atlast, the data revealed long, straight boundaries where one spectral signature ended and another began. Instead of fading gradually, materials on ThreeI Atlast changed in sharp lines, as if panels with different compositions touched edge to edge. In several regions near mid-latitude, circular gaps cut cleanly through the shell of ThreeI Atlast. Each opening in Atlast measured on the order of a few hundred meters across nearly perfect circles within the limits of observation. Other circular structures clustered toward a pattern that loosely suggested rings and hexagons repeated around the body of ThreeI Atlast. Natural impacts and venting usually leave jagged scars and irregular pits, not a network of shapes that echo simple geometry. Modelers tried to reproduce the appearance of Atlast by letting fractures propagate ice sublimate and chunks fall away at random. Under those conditions, the surfaces of simulated bodies rarely lined up into straight borders or evenly spaced circles the way ThreeI Atlast does. When probabilities were estimated for such symmetry arising by chance, some approaches returned odds so low they became difficult to treat as comforting. A universe governed by physics can in rare cases carve order out of chaos, but ThreeI Atlast seems to cluster those rare cases together. For conservative readers, the geometry on Atlast remains a puzzle awaiting a better natural mechanism. For others, the repeated lines and circles on ThreeI Atlast look uncomfortably similar to seams and ports on a constructed shell, a pattern that quietly challenges the assumption that this visitor is only a sculpted fragment of ice. For months, the electromagnetic field linked to ThreeI Atlast behaved like a quiet metronomic heartbeat in the low-frequency band. Waveforms tied to Atlast repeated with such regularity that analysts began treating the pattern as a fixed background in their models. On October 21st, roughly a day after the most sensitive observatories focused together on ThreeI Atlast, that heartbeat changed. The once smooth carrier from Atlast fractured into packets, short bursts of signal separated by precisely timed stretches of relative silence. New measurements showed ThreeI Atlast sending trains of energy about 3.7 seconds long, followed by gaps close to 89 seconds. Noise inside each burst dropped, sidebands sharpened, and the modulation scheme no longer matched the earlier simpler field around Atlast. Teams cross-checked power grid interference, solar activity, and instrumental artifacts, searching for a terrestrial cause that might explain the shift away from Atlast. Those checks failed to remove the correlation between the new pattern and the moment when high-gain dishes and Webb-class optics turned toward ThreeI Atlast. A few researchers began to speak carefully about sensing, wondering whether ThreeI Atlast could register the focused attention of many detectors. In that line of thought, materials or circuits inside Atlast might sit near quantum limits, reacting measurably when streams of incoming photons rise above a threshold. Such a system would blur the line between observation and interaction, turning every deep look at ThreeI Atlast into a kind of quiet knock on the door. For cautious minds, the data still allow natural explanations, yet the timing and structure of the change leave ThreeI Atlast feeling less like a passive rock and more like a device that knows in some limited way when it is being watched. When the new modulation from ThreeI Atlast settled into a steady rhythm, the numbers became a puzzle. Analysts fed the timing of each burst and each pause from Atlast into software built to hunt for structure. The trains from ThreeI Atlast lasted about 3.7 seconds, followed by silences close to 89 seconds. When the ratio of burst length to gap length was computed for Atlast, the result hovered at 0.004153. On its own, that value meant nothing until someone compared the figure from ThreeI Atlast with tables of planetary properties. There, in a catalogue of masses, the same sequence of digits quietly appeared as the mass of Earth, divided by the mass of Jupiter. Teams tried to see whether ThreeI Atlast had simply wandered into one of many possible numerical coincidences. They checked orbital periods, rotational rates, and other constants to see how often random data would echo a familiar ratio around Atlast. The searches rarely turned up matches as clean as the mass fraction shared between Earth-Jupiter and the signal chained to ThreeI Atlast. For cautious minds, the safest stance was to call the alignment another entry in a long list of curiosities around Atlast. For others, the simplicity of the fraction suggested that ThreeI Atlast might be broadcasting the layout of the local system in the language of gravity. If that reading holds, Atlast is not speaking in words but in relationships any advanced physics must learn. The idea that ThreeI Atlast is sending a deliberately chosen number sits on the edge between comfort and unease, Such a message would mean Atlast carries a model of our neighbourhood and expects someone here to decode it. Yet no law of statistics has been broken, and the data still allow the possibility that ThreeI Atlast has by chance lined its internal clock up with the weight of our worlds. By the time researchers mapped the post-perihelion trajectory, ThreeI Atlast no longer looked directionless. The outbound curve of Atlas, shaped by solar gravity and measured jets, bent gently toward Jupiter's domain in 2026. Simulations from multiple groups agreed that ThreeI Atlast was on course to graze the Jovian system around March of that year. On separate planning charts, mission profiles for ESA's JUICE spacecraft listed a critical orbital insertion maneuver at almost the same time. The overlap between the arrival of Atlast and the scheduled presence of JUICE near Jupiter startled engineers and dynamicists alike. Under ordinary expectations, an interstellar wanderer like ThreeI Atlast should ignore the sparse hardware humans park around giant planets. In this case, the refined path of Atlast threaded close to a corridor where a functioning observatory would already be waiting. That geometry encouraged some teams to ask whether ThreeI Atlast was simply drifting through, or whether coordination with existing infrastructure was part of a deeper plan. Statistical analyses attempted to quantify how often a random trajectory would shadow a major mission within a narrow time window. Many runs still allowed coincidence, yet the stacked context around Atlast energy core, unusual shell-encoded ratios made the timing harder to dismiss as pure chance. To scientists used to seeing humanity as a bystander, the idea that ThreeI Atlast could be aiming for our instruments reversed the usual roles. Instead of pointing telescopes at an indifferent universe, humanity began to feel more like a subject in someone else's long experiment whenever Atlast crossed a plot. If that interpretation holds, ThreeI Atlast treats the solar system less as a landmark and more as a field site under periodic review. Such a posture would mean visitors like Atlast do not arrive as equals searching for conversation. They arrive as long-range surveyors who may have watched worlds like ours for decades or centuries, waiting until our technology grew bright enough to notice that they were already here. Long before the details of its interior were known, the sheer motion of ThreeI Atlast marked it as something unusual. Tracking stations watched Atlas cut across the solar system at nearly 37 miles per second, a pace too fast to be captured for long by the Sun. Orbital calculations wrapped around ThreeI Atlast produced an eccentricity between about 6.1 and 6.2, numbers that high place Atlast on an open hyperbolic path, not on an ellipse, confirming that ThreeI Atlast is not bound to our star in the way ordinary comets are. For most visitors of that kind, mass estimates are small, their bodies little more than drifting shards. When astronomers folded together brightness, distance and reflectivity for ThreeI Atlast, the implied size grew far beyond those modest expectations. Reconstruction suggested that Atlas carries more than 33 billion tons of material, a bulk that changes how its story feels. At an estimated diameter exceeding 3 miles, ThreeI Atlast stands more as a moving mountain than as a speck of debris. In comparative terms, Oumuamua, the first known interstellar object, was almost delicate beside ThreeI Atlast. Depending on which model is used, Atlast outweighs Oumuamua by a factor of 1,000 to 100,000. That ratio means that if Oumuamua was a narrow shard, then ThreeI Atlast is a whole ridgeline passing through the dark. The hyperbolic orbit of Atlast already tells us that this mass began its journey around another star. Together, the speed and trajectory show that ThreeI Atlast is a true interstellar traveller, visiting once before, vanishing back into galactic space. A body that massive has survived long crossings through the thin dust between systems, quietly accumulating a record of impacts and radiation along its skin. From a dynamic point of view, ThreeI Atlast could still be one more fragment shaken loose from distant formation events. From a human point of view, the thought that such a large, fast-moving structure has entered and will leave our neighbourhood only once adds a weight of its own. 3. Atlast becomes not just a data point in a catalogue, but a singular encounter with a scale of object that rarely comes close enough for our instruments to truly see. Water in space is usually a reassuring sign, a gentle tracer of heat and sunlight at work. For ThreeI Atlast, the way water appears around the visitor has become one of the strangest clues. In October 2025, NASA's Swift Observatory measured ThreeI Atlast releasing water at about 88 pounds per second. The plume from Atlast rose as a continuous spray, more like a fire hose than a faint exhale from frozen rock. At that time, ThreeI Atlast still lay beyond the frost line where ordinary comet ice should remain locked and quiet. Under standard models, sunlight at that distance cannot drive such vigorous outgassing from Atlast without quickly stripping the exposed layers. Either buried reservoirs were being opened in an orderly sequence, or ThreeI Atlast held an unexpected source of internal heat. Instead, the power behind the escaping water from ThreeI Atlast appeared steady over many rotations, as though a regulated engine were maintaining pressure. That language of an engine remained speculative, yet the jet geometry around ThreeI Atlast began to resemble more than random venting. Some streams from Atlas pointed roughly opposite the direction of travel, contributing a small but persistent push in trajectory calculations. To engineers familiar with chemical rockets and ion drives, the idea of an ancient object like Atlast gently throttling through space feels thrilling and unnerving at once. ThreeI Atlast starts to look less like a passive stone falling down a gravitational well, and more like a craft managing its own descent through the inner system. Conservative voices still search for unfamiliar natural reactions inside ThreeI Atlast, combinations of volatiles and structure that might mimic deliberate propulsion. Until such a mechanism is found, the high sustained water loss beyond the frost line keeps ThreeI Atlast hovering at the edge of the artificial drive hypothesis. The numbers do not prove a constructed engine, yet they refuse to let ThreeI Atlast settle comfortably back into the category of a simple, uncontrolled comet. On clear nights above Mauna Kea, the Keck 2 telescope spread the spectrum of ThreeI Atlast into thin coloured threads. In those threads, ThreeI Atlast revealed bright emission lines from nickel streaming away in the gas around the visitor. Under ordinary expectations, nickel and iron are born together in stellar furnaces and locked side by side into dust and rock, but ThreeI Atlast broke that partnership. Observers watching ThreeI Atlast saw nickel features stand out cleanly, while the corresponding lines for iron stayed stubbornly absent. Comets in our own system carry both metals traces of ancient supernovae mixed into their cores, yet ThreeI Atlast seemed to favour one child of that process and discard the other. Analysts tried to force models in which selective heating phase changes or unusual grain sizes around ThreeI Atlast could free nickel first while holding iron back. Those attempts bent the physics hard, and still the spectra of ThreeI Atlast refused to match a clean natural pathway. On Earth, when humans separate nickel from iron, they do so inside refineries and reactors, turning ores into alloys for turbines, engines and heat shields. The pattern around ThreeI Atlast reminded some chemists less of a primitive comet and more of slag and feedstock in an industrial chain. In that analogy, ThreeI Atlast would not be a raw lump from a forming system, but a piece of something that has already passed through stages of selection and design. Conservative voices warned that unfamiliar geologic or cryogenic processes might yet explain why ThreeI Atlast exhales nickel alone. Others felt that each new attempt to rescue a natural scenario for Atlast only deepened the sense that a hidden machine may have touched this material before it was sent away. The data do not prove factories or foundries, yet the missing iron leaves. ThreeI Atlast carrying a chemical accent that sounds uncomfortably like the language of industry. From a distance, the tail of a comet is supposed to point away from the sun like a banner driven by light and wind. Observers following ThreeI Atlast saw something less obedient. Images of ThreeI Atlast showed a bright anti-tail extending roughly back toward the sun, a spear of dust and gas leaning into the very pressure that should push it away. Models of radiation forces could bend streams and curve plumes, yet the configuration around Atlast stayed stubbornly inverted. When dynamicists overlaid the full path of ThreeI Atlast onto the clockwork of the inner planets, the odd geometry deepened. Across its passage through the inner system, ThreeI Atlast passed strikingly close to the orbital tracks of Mars, Venus and Jupiter. The three near approaches lined up in a way that left very little room for casual drift. Running large ensembles of random hyperbolic orbits, teams asked how often an interstellar visitor like ThreeI Atlast would by chance skim past that many worlds in a single transit. The probability estimates settled around a few thousandths of a percent, with one recurring figure near 0.005. That small number did not forbid coincidence, yet each new anomaly around ThreeI Atlast made reliance on coincidence feel thinner. To some analysts, the pattern suggested that ThreeI Atlast might be using planetary gravity as waypoints, slipping through regions where sensors, habitats and future missions are densest. In quiet discussions, a metaphor from warfare resurfaced, and ThreeI Atlast was compared to a Trojan horse in orbital form. In that reading, ThreeI Atlast wears the expected costume of a comet, while following a track that behaves more like a survey of inhabited or strategic zones. Skeptical minds still prefer to treat ThreeI Atlast as an extreme but natural outlier, drawn from a vast population of unseen objects. Yet the combination of a reversed tail and a thread of low-probability encounters leaves 3I Atlas standing at the uncomfortable boundary where random chance starts to look like deliberate aim. When the first papers on 3I Atlast appeared, they read like careful invitations to consider an uncomfortable possibility. The authors framed Atlast as a statistical outlier that might at the 30 to 40% level belong outside the catalogue of natural bodies. Those numbers did not claim certainty. They simply marked a region where the behaviour of 3I Atlast strained existing models. Responses arrived quickly. A prominent team in the search for extraterrestrial intelligence argued that every oddity linked to 3I Atlast could, in principle, be folded back into chemistry and geology. In their view, rare outgassing regimes, unfamiliar ice structures, and complex fragmentation might collectively explain the signals we see from Atlast. The paper treated 3I Atlast as a stress test for imagination inside natural astrophysics, not as evidence for any kind of technology. Supporters of the original analysis replied that each new natural scenario demanded more layers of special conditions around 3I Atlast. They pointed out that invoking multiple unlikely processes to rescue a comfortable conclusion is a pattern scientists usually try to avoid. 3I Atlast, they argued, should be treated the same way. If data bend simple models, the models must move first. At the heart of the debate sits a simple rule. Science is supposed to follow measurements even when they steer thought into regions that feel speculative or unwelcome. In that spirit, 3I Atlast becomes less a verdict about aliens and more a mirror held up to our habits. If researchers refuse to entertain artificial explanations for Atlas purely because such explanations feel too strange, the field risks turning away from the very anomalies that carry new information. The most cautious voices now suggest a middle path. 3I Atlas should remain under active observation with every reading labelled clearly as fact or speculation, while theories stay flexible enough to absorb whatever Atlast reveals next. On that path, the purpose is not to prove technology or to deny it in advance, but to let 3I Atlast teach how complex and how surprising the universe is willing to be. When 3I Atlast swung in toward the Sun, the meeting of light and ice rewrote expectations in a matter of days. Solar physicists were already on alert because the encounter unfolded during a period of solar maximum when the star itself was unusually restless. Coronagraphs were trained to block the Sun's glare and reveal the faint halo around 3I Atlast as the visitor approached perihelion. In early frames, Atlast glowed at a level that fit comfortably with a large distant comet making its way inward. As days passed, the brightness curve for 3I Atlast began to steepen beyond familiar shapes. Instead of rising by a factor of 10 to 100 as many comets do near the Sun, the luminosity tied to Atlast climbed toward an increase of roughly 400 times. Graphs that usually show gentle slopes for dusty bodies near perihelion now showed 3I Atlast shooting upward like a flare. Each new data point pulled the line higher, and the comparison to ordinary behaviour grew more strained. Teams checked for instrumental ghosts scattered light and processing errors that might falsely amplify 3I Atlast on their screens. Those checks returned clean, leaving the amplification as a property to be assigned back to Atlast itself. Some researchers suggested that unusual reservoirs of fresh ice on 3I Atlast might have been exposed all at once, giving a short, brilliant surge. Others pointed out that even energetic outbursts rarely maintain such a dramatic enhancement, without tearing fragile structures apart. The result was a picture in which 3I Atlast did not merely brighten in step with solar heating, but appeared to overachieve, behaving as though additional mechanisms were helping sunlight turn the visitor into a temporary beacon. From that point on, every discussion of the perihelion passage of 3I Atlast carried the sense that the object had used its time near the Sun to reveal a side of its nature that simple comet analogies could no longer comfortably hold. When observers first turned wide-field cameras toward 3I Atlast in early summer, the reflected light looked comfortably familiar. 3I Atlast presented a predominantly red hue, the kind usually associated with dust-darkened ice and long exposure to cosmic rays. As weeks passed and 3I Atlast moved inward, narrowband filters began to show a softening of that red toward a curious green. By early September, Atlast carried a distinct emerald tint, as if fresh gases were starting to glow around the visitor. Closer to perihelion, the story shifted again. Spectra and colour composites now showed 3I Atlast drifting toward deep blue, with emissions from certain molecules rising in strength. In standard comet behaviour, heating and dust release tend to push colours in the opposite direction, making bodies redder as small particles dominate scattering. 3, Atlast seemed to walk backward along that usual gradient, trading the warm end of the spectrum for colder shades as solar input grew. Some teams proposed that 3I Atlast might be fragmenting, exposing new layers whose chemistry would naturally favour blue emissions. That explanation began to fray when 3I Atlast reappeared after perihelion with the main nucleus still intact and structurally coherent. Other models tried to invoke unusually pure jets or exotic ices to carry Atlast through such a smooth progression from red to green to blue. In every case, the physics had to work harder to keep pace with the measured colours around 3I Atlast. The end result is a colour curve that reads more like a designed sequence than a random response, even if no design can be proven. 3I Atlast moved on from the Sun, leaving behind a record in which brightness and hue together whisper that this object does not merely brighten. Atlast changes character in ways that resist being folded back into the most comfortable comet scripts. When the trajectories of comets are mapped, gravity is supposed to write almost every line. For 3I Atlast, the lines began to slip. Astrometric fits showed that 3I Atlast was not quite where a purely gravitational orbit said Atlas should be. To match the actual positions of 3I Atlast on the sky, models had to add a small extra push, a non-gravitational acceleration tied to the visitor. Near perihelion, that additional term reached values on the order of 200 km per day in effective speed. For comparison, the interstellar comet Borisov needed roughly half that correction, and the famous Hale-Bopp required almost 2 orders of magnitude less. 3I Atlast by those measures sat at the top of the chart, behaving as though some internal process were helping pull Atlast away from the path. Gravity alone would dictate. Standard explanations tried to rescue 3I Atlast with asymmetric outgassing, allowing jets of vapour and dust to act like small thrusters. Under that approach, sunlit regions on 3I Atlast must vent more strongly in specific directions, giving Atlast a consistent nudge each rotation. The difficulty came when jet strength rotation and thermal models were combined. The numbers demanded unusually coherent, persistent sources on 3I Atlast, fine-tuned to produce the observed drift without tearing Atlast apart. For cautious voices, the safest language was to say that 3I Atlast experiences extreme non-gravitational acceleration, whose source remains unclear. For others, the behaviour of 3I Atlast resembles controlled thrust more than random venting, as if Atlast adjusts its own movement through the inner system. No single equation proves engines or guidance, yet every refinement of the orbit keeps 3I Atlast in the narrow zone where gravity alone is not quite enough, and some additional influence appears to be at work. In the days after, perihelion images of 3I Atlast began to show a new kind of structure. Instead of a single hazy fan, the core of 3I Atlast sprouted narrow beams of gas that cut cleanly into space. Careful processing revealed at least 7 separate jets anchored near the nucleus of Atlast, each one holding its own line. Some streams from 3I Atlast leaned outward along the expected anti-solar direction, but others tilted in unexpected angles, even partially sunward. Brightness profiles along those jets did not blur together the way ordinary comet plumes often do. 3I Atlast maintained distinct strands as if each outlet were gated or constrained by a separate channel inside the body. Rotation studies showed that 3I Atlast spins turning different faces toward the Sun over time. If the jets on Atlast were simply random weak vents, rotation should smear them into a broad blended fan. Instead, the 7 primary structures around 3I Atlast stayed surprisingly narrow, holding their shapes over many frames. To reproduce that persistence, models had to give 3I Atlast either unusually strong collimation or a network of stable, long-lived nozzles. In more speculative sketches, internal conduits inside 3I Atlast begin to look less like cracks and more like plumbing. Under that lens, each jet on Atlast behaves like a controllable outlet contributing force, while preserving separation from its neighbours. Conservative analyses still treat the pattern on 3I Atlast as an advanced problem in cryovolcanism and fracture mechanics. Yet every new stack of images reinforces the impression that 3I Atlast is managing multiple flows in parallel rather than shedding gas in a simple chaotic burst. The picture that emerges is of a visitor whose breath is not a single sigh, but a carefully segmented exhale sculpted into space. As days passed, the 7 narrow jets around 3I Atlast began to blend. Streams that first left Atlast as separate beams slowly braided into a single massive plume stretching away from the nucleus. In processed frames, a second structure appeared an anti-tail from 3I Atlast, reaching roughly 1 million kilometers back toward the Sun. Under such forces, a fragile body should shed chunks or fracture outright. Yet Atlast emerged from perihelion with its main core intact. Brightness and dynamics together suggest that ThreeI Atlast may span up to 10 kilometers across a size that helps Atlast endure the violent heating and loss of material without coming apart in full view of the instruments watching. Taken as a whole, the behavior of ThreeI Atlast no longer resembles an average member of any familiar population. The mass, the engineered-looking shell, the strong internal field, and the extreme non-gravitational acceleration all stack in favor of Atlast being an outlier. For a body as large as 3I Atlast to survive billions of years in interstellar space without shattering is already improbable. For that same body to pass close to the Sun precisely during the brief era when our instruments can resolve Atlast in such detail pushes the odds lower still.